Hello everyone, my name is Mohamed Lechiakh. I'm a PhD candidate from Mohammed VI Polytechnic University in Morocco, and I'm going to present this joint work with Alexandre Maurer, which is entitled FEBR, which is an expert-based recommendation framework for beneficial and personalized content. So first of all, I will start by a general introduction in which I will introduce the problem, then our contribution, and then our research scope. Then I will move to present the proposed solution. Then I will move to talk about our simulation settings and models and the experimental results. And then I will end up by a conclusion and presenting some future works. So first, let's take this example of a user who is trying to get some information from YouTube about COVID-19. And as you can see, the recommender engine give him a list of videos, and the user is a little bit confused about which video he will first take from this list. Is it the first one, which is the first ranked one, or is it the second one that has millions of views, or is it the third one that actually comes from a trusted organization? So this is from the user perspective, and from the recommender perspective, and we take YouTube as an example. YouTube has more than 2 billion of users with 70% of total watch time is only based on algorithmic recommendations. So these high numbers implies a very big problem, which is how YouTube and other big recommendation platforms deal with the amount of harmful and misleading content on their platforms. In other words, how these recommendation platforms succeed to or ensure high quality and beneficial recommendation for their users. So indeed, YouTube has adopted in the last years many strategies and policy controls in order to combat this problem, but the problem still persists, and there is a lot of anxieties from the research community as well as the business community in order to efficiently address it. In our case, we are trying to address the recommendation quality from the two aspects, from the personalized and the beneficial aspects. And we mean by a beneficial content, a content that is accurate, educational, interesting, trustworthy, practical, and so on. It means all the quality factors that describe a correct content. But now the problem of today algorithmic recommendation and most of traditional recommendation systems is that they only succeed to optimize the personalization services because they rely on algorithmic recommendation that use intrinsic metrics like the number of clicks, number of watch time, the number of like and dislikes, which only leads to these personalizations, but they really fail to provide robustly beneficial results. This is why we ask this question: how can we build beneficial and personalized recommendation system at the same time? So our contribution is inspired from this intuition. We take a set of experts which is well chosen, and we try and we ask them to provide a evaluation behavior within a recommendation environment, and it's like each expert will make his own selection of videos and evaluate them, and the idea is to use some machine learning techniques in order to capture these expert trajectories and to learn the dynamics and the intuition behind them in order to push users to mimic such behaviors and to make such expert choices, because we assume that expert recommendation we assume that these expert recommendations are most likely to provide high quality recommendation. So this is why we propose an apprenticeship learning based framework using inverse reinforcement learning. And before explaining these concepts and our proposed solution, let's first point out our research scope. So first, the way we select expert is out of the scope of this work, and it could be discussed at the system management level. Also, simulation with real dataset is very challenging. This is why we perform simulation with synthetic data using RecSim. The problem with the real dataset is that as we use online on policy algorithms and expert environments which require online interaction with the environment. This is why simulation with the static dataset would not be efficient in providing this interactivity. And also, simulation with the static datasets is not efficient because this logged data don't record the main patterns and factors of experts, which are very important for our approach in order to recover their behaviors. So we built our framework on RecSim, which is a powerful famous reinforcement learning based recommendation framework developed by Google Research Labs, and we validated our claims and our results using scientific data. Also, we note that the choice of RecSim is not a limitation of our approach, which could be re-implemented using other similar reinforcement learning based recommendation frameworks. Now, as a background of our work, so first we have the reinforcement learning model that takes an agent that interacts with a Markov decision process environment, and which generates the next states and the reward. And the reward in this case are totally known, and it could be explicitly designed. But the opposite, when we talk about inverse reinforcement learning, the reward is typically unknown. This is why the agent is just observing a set of demonstrations that are coming from experts, and based on this demonstration, the agent tries to recover the unknown reward function. And when this reward function is simultaneously used to optimize its associated optimal policy, then we talk about apprenticeship learning. So this is a simple difference between these three imitation learning techniques. Now we have our B components FEBR model framework, and as you can see, we have two components. At the left we have our expert components, which is responsible of generating the expert trajectories within the expert environment, and these trajectories will be taken by the IRL max-int model in order to generate the optimal expert policy, which will be taken with the SACE datasets into the user recommendation components in order to train an expert-based agent that mainly optimize a user policy, which will be used for recommendations. We will discuss these components more on details in the next slides. But before that, let's first talk about this important notion in our work, which is the quality. As in many recommendation systems, these systems use a scoring model in order to rank items inside their systems. And in our approach, we further take these scores, which are called qualities, So they are taken by FEBR and differently updated in its components. For example, in the expert components, when an expert evaluates a video, then the new quality of this video will be the average of the rating features of this video. And the user recommendation environment, when the clicked video by the user is already evaluated by an expert, then its quality is exactly equivalent to this expert quality. Now, our expert ER/IR component is composed with these components. First, we have the expert MDP environment, and this MDP is without a reward because we are using inverse reinforcement learning. So in this environment, we specify the user and the document and the response models, and we specify a configurable evaluation model in order to capture the evaluation given by the expert for videos. Also, after behaving in this environment, the expert generates trajectories, which are exactly the sessions, and they are a series of state actions pairs. And inside the IRL model, first we define the unknown reward function, which is assumed to be linear. So we have the weight vector multiplied by the virgin feature vector. So, and then we calculate the feature counts for each trajectory, and then we calculate the average feature counts over all these trajectories. And then we use the principle of maximum entropy in order to fix a probability distribution over the set of trajectories that maximize this entropy with respect to this matching property, because our objective is to find this probability that satisfies this property, this equality. And why we use this principle of maximum entropy? Because it provides the most likely statistical probability distribution that generates or that constructs consistent trajectories based on the non-commuter reward. And we mean by non-commuter reward a reward that exactly matches the feature counts, this feature counts property, without any additional assumptions or preferences above the demonstrated behavior. And we are using also for this part of reinforcement learning algorithm, we are proposing within our framework two algorithms, value iteration and policy iteration, but we are using in our simulation value iteration that has proven better convergence results. The user error recommendation component uses first a classification state model that match each user state to its closest expert state using a similarity metric, which is here the cosine similarity, and otherwise it just returns 0. And we also define this user recommendation expert based policy defined by this structure, and it will be optimized by this k-learning expert based recommendation algorithm, which has these two important blocks. The first one is will be accessed when we have a successful matching of the classification state model. So in this case, the recommended slate will be the slate returned by the optimal expert policy. Otherwise, the algorithm is just optimizing the local user policy based on the classical body of the k-learning algorithm that maximizes a key function. And at the end, we update our user recommendation expert based policy by the optimizing the slate returned from the above conditional blocks, and we continue this till the convergence of this algorithm. So our simulation environment is developed using RecSim framework, and we highly recommend you to refer to our paper and also to RecSim paper for more details about these models. And you can also find our source code here on GitHub for more details about the implementation. For the settings, we use a global system configuration settings here, which is common for the two components, and for the EL-IRL components, which run our optimal expert policy using 100 experts. And the user recommendation components, we used two phases, a training phase in order to train the optimal user policy, and then we used a testing phase with 1000 of testing session for each user in order to test this optimal policy optimized by the algorithm. And then we fixed also the threshold of the classification model to be equal to 0.5. Now for the baseline approaches, we used 4 baselines that generally reflects the behavior of classical reinforcement learning based recommendation algorithm that try to maximize a reward function in order to optimize the learned actions of the policy. So here the first 3 baselines don't use the evaluation of experts, and they are used in order to evaluate the performance of our approach to provide high quality recommendations. And the last one use a random agent to recommend slates from the corpus of videos with high expiration. It is used in order to test the ability of our approach to provide personalized recommendations. The evaluation metrics now, we use the average social quality QT, and we use the average experience quality QE, which is returned when a watched video by a user when this watched video is already evaluated by an expert. And we have these two engagement metrics. And the first one is the average clicked videos, and the second one is the total watch time. And we also consider this assumption, so that the notion of quality of the baseline methods of this especially for the baseline that don't use expert evaluation, we consider that this notion of quality reflects the same information as our approach, even when our approach returns qualities that has been evaluated by experts. So now the results show that from one side, as you can see in the left figure, our approach leads to positive consumption of quality by providing positive quality of the expert-based quality, which always exceeds and overcome the total quality, which means that the learned expert policy provide high performance. And also the right figure, you can see that our approach provides significant gain of term of average total quality compared when comparing to the other baselines. Also, we can confirm that our approach provides almost closer values of the engagement metrics when comparing with the other baselines, which proves that our approach succeeds to maintain a high level of engagement. To summarize, simulations show the efficiency of our approach to control the quality of recommended content while keeping high engagement rate. Also, FEBR efficiently leads to positive quality consumption when following the expert policy, and also it succeeds in learning an expert-like policy through its EL IRL components, and also the constructed key learning algorithms can effectively optimize a high-quality long-term user policy, which recommends beneficial and evaluated content. And also the results shows an important remark here. They show that a small percentage of beneficial videos can provide a considerable gain in quality following an optimal expert policy, as it is shown here in the left figure, because this decrease the quality from the blue curve to the red curve. And for future works, we think that it would be interesting to propose a decentralized version of FEBR to scale to system of large dimension using less constraints on the reward function. It would be also interesting to extend this work to study the case of unreliable experts, and also it will be interesting to propose some solution to mitigate the effects of the cold start problems, and it would be also interesting to run these simulations in a real life conditions. So that's the end of our presentation, and thank you very much for your attention.